Find the image of the set under the given transformation. S is the triangular region with vertices 0, 0, 1, 1, 0, 1. And then after the semicolon, those are the transformation equations. So this guy will map actually S to R points. So U and V are points in S, right? And then out pops X and Y. So these transformation equations will define T, something that maps S to R. So T of UV, the input is U and V, the output is an ordered pair in the XY plane inside R, or possibly on the border. So I don't know, I'm going to give you a little more for your tuition dollar here and graph this thing. I don't know if we need to do that. I think that's how I presented the answer, though, if I remember right. So if we graph the triangle, this is in S always stands for the UV plane. So this is in the UV plane. Let's graph that. So 0, 0 we could put here. Maybe 1, 1 would be here. And or that would be 0, 1 rather. And then maybe 1, 1 would be here. Something like that. And so if we connect those dots, then the interior of this triangle is what we're calling S. Does that make sense to you? Okay, and then let's get the equations then associated with the line segments I just connected. What would be, I guess the most complicated equation would be the diagonal here. What would that be? V equals just U, right? Because it goes from 0, 0 to 1, 1. So it's like Y equals X. It's the 45-degree line in the first quadrant. And then what would this vertical line be? It would be U equals just 0, right? It's on an axis. And then this, you were talking about the horizontal line. It would be V equals 1, right? Does everybody see where those are coming from? Okay, so the idea then is we know the UV equations, don't we? So that we know the UV equations that define the boundary of S. And we would like to get the XY equations, the corresponding XY equations via this transformation that corresponds to the boundary of R. So let's write down our equations. We know from what I drew over here that V equals 1, U equals 0, and V equals U. Well, let's do the ones with U in it, or the one with only U in it. So if X equals U and U equals 0, then X equals 0. Does that make sense? So we're saying that this U equals 0 is going to map directly to the same line segment, or the analogous line segment anyway, in the XY plane. Now what about V equals 1? That's okay. Let's be careful here. If Y equals V squared, what does V equal? Radical Y. And I suppose you could make an argument plus or minus, but the corners, these vertices are going to map to points in the first quadrant in the XY plane. So I think we're only going to need to consider the positive root. If you don't believe that, just try this guy, 1, 1. Where's that going to map to? So this is U equals 1, V equals 1. That's going to map to X equals 1, Y equals 1, right? So I don't think we need to consider the negative root here. So then if V equals 1, we could say what? The square root of Y equals 1, or just Y equals 1? Would you buy that? Okay. And then V equals U would be like saying what? The square root of Y on this side equals X on this side. Or if you square both sides, Y equals X squared. So I'm going to say that these guys are my transformed boundary equations for my region R in the XY plane. Does that make sense? And once you realize that, I mean, you could graph the result if you want. I think that's how I presented the answer. So now the xy plane, okay, x equals 0. By the way, as I started to say earlier, the vertices are going to map to vertices, okay? So we can be pretty sure then of the the vertices of our new region. We can be pretty sure that 0, 0 via this transformation, x equals u and y equals v squared, u equals 0, v equals 0 is going to map to 0, 0 squared is 0. So 0, 0 is going to map to 0, 0. And in fact, 1, 1 will map to 1, 1 because when you square 1, you get 1. So 1, 1 might be here. And then 0, 1, same reasoning, will map to 0, 1. So the vertices actually don't change under the transformation. And, well, x equals 0 really looks the same as u equals 0 when you graph it, right? Let me see if I can make it show up in orange there, right? So x equals 0, that piece. And then, oh, y equals 1. Well, that's going to look the same as v equals 1, isn't it? And then, so the thing that changes this, if you think about this hypotenuse here, that hypotenuse changes from a line segment to part of a parabola, doesn't it? So think of it morphing. As you go from uv to the xy plane, the hypotenuse changes from linear to quadratic, something like that. And then, so that would be the boundary, and then in here then would be r. So this would be y equals x squared. And that's all you were asked to find in that one. So just this region here.